Hello everyone, this is Fab. We are going to start another series of thermodynamics. In this lecture, we will cover thermodynamics process of perfect gas. In this lecture, we will cover specific heats of gases, a relationship between specific heats, and two thermodynamic process of perfect gases, including isochoric process and isobaric process. Let's start from specifics of gases. As we know that from experience that it takes different amounts of energy to rise the temperature of identical masses of different substances by 1 degree. For example, we need about 4.5 kg of energy to rise the temperature of 1 kg of iron from 20 to 30 Celsius, whereas it takes 9 times this energy, about 41.8 kg to be exact, to rise the temperature of 1 kg of water by the same amount. Therefore, it is desirable to have a property that will enable us to compare energy storage capabilities of different substances. This property is the specific heat. The specific heat is defined as energy required to rise the temperature of unit mass of substance by 1 degree. In general, this energy depends on how the process is executed. In thermodynamic process, we are interested in two kinds of specific heats: specific heat at constant volume and specific heat at constant pressure. Physically, the specific heat at constant volume Cv can be viewed as, the energy required to rise the temperature of unit mass of substance by 1 degree, as the volume is remain constant. The energy required to do the same pressure is maintained constant in specific heat at constant pressure. So whenever we will deal in the constant pressure, the pressure of the system will remain constant, and this help us to understand that it also increase the internal energy of the system. In this figure, we can see two jars having a 1 mole of gases and other have a 1 mole of gases. One of them is at constant pressure, other one is at constant volume. Whenever heat is supplied at constant pressure, the volume of the system may change. It means to say the internal energy of the substance will remain same, but volume of the system may be changed, and definitely it will change. On other hand, when we talk about the Cv, constant volume, once heat is supplied to the system, internal energy of the system may increase. Define that randomness inside the molecules will increase. It also concluded that once pressure of the closed system will remain constant or increase, volume remain constant. That define that pressure will increase at constant volume, as well as entropy of the system will also increase. This is how specific heat at constant volume defined. It is the amount of heat required to rise the temperature of unit mass of gas to 1 Celsius when substance heated at constant volume. It generally denoted by Cv. The total heat supplied at constant volume can be defined mathematically Q is equals to mass multiplication with specific heat at constant volume and change in the temperature. So here Q is equals to mCv T2 minus T1. M is equals to mass and Cv is specific heat at constant volume. Ti is the initial temperature. T2 is the final temperature. T2 is always greater than T1. Let's define specific heat at constant pressure. It is the amount of heat required to rise the temperature of unit mass of gas through 1 Celsius when substance heated at constant pressure. It is generally denoted by Cp. Mathematically, we can define as Q is equal to mCp T2 minus T1. T1 is the initial temperature of gas, T2 is the final temperature of gas, and Cp is the constant pressure. M is the mass. In this figure, we can see that a slow system where pressure is a constant. Once heat is changed or heat is supplied to the system, volume of the system will change, as we can see PV diagram. But here pressure remains constant. The relation between specific heat, the difference between two specific heat is equals to gas constant, or Cp minus Cv equals to, or the relation the ratio of two specific heat Cp minus Cv is known as adiabatic index, and it is represented by a Greek letter gamma. Cp, mathematically we can define it as Cp minus Cv is equals to, or where Cp by Cv is equals to 1 plus R minus Cv. After simple rearrangement, we have a final equation gamma is equals to 1 plus R by Cv. Since Cp is greater than Cv, therefore the value of gamma is greater than unity. The value of gamma for air is 1.4. Now we are going to start about thermodynamic process of perfect gases. So the thermodynamic process is the process of heating or cooling of gas is defined as a thermodynamic process. During the process, properties of gases change, such as pressure, temperature, enthalpy, entropy will change. Constant volume process or isochoric process. In this process, volume of the system will remain constant. Whenever a gas is heated at a constant volume, its pressure, temperature will increase. Since no change in the volume, no work done by gases. All heat is stored by gases that rise internal energy of the system. Suppose m kg is mass of certain gas is heated at constant volume from initial temperature T1 to final temperature T2. This process shown in process volume diagram in the previous slide. We have a equation heat supplied Q1 to 2, U is the internal final energy minus U1 initial internal energy, work from 1 to 2, where work is 0, then U2 internal energy minus U1 is equals to mCv T2 minus T1, where is it Q12 is equals to U2 minus U1, which is equals to mCv T2 minus T1. Here we can see in PV diagram for isochoric process and PV diagram of isochoric process. Once pressure of the system increase, its temperature will also rise. Here volume of the system will remain constant. there is no work done by the gases. In PV diagram we can see that pressure of the system is gradually increasing due to supply of heat. Once heat is uh, removed from the system, volume of the system will also decline. In other words, it's also follow the Boyle's law, which is equals to P is directly proportional to T, where volume is the constant pressure process or isobaric process. When gas is heated at a constant pressure, its temperature and volume will increase. Since there is no change in its volume, the heat supply is utilized in increasing the internal energy of gases. Also, for doing external work, it may be noted that this process is governed by Charles' law. Now consider m of the mass of certain gas being heated at constant pressure from initial temperature T1 to final temperature T2. This process is shown in PV diagram and the next slide. As we know that heat supplied to the gas at constant pressure, mathematically we have a same formula of constant isobaric process, which we have already learned in previous slide, that Q1 to 2 m is equals to mass Cp is constant pressure T2 minus T1. Note here, during the expansion or heating process, work is done by the gas and internal energy of gas will decrease. Change in internal energy will negative, and heat supplied to the gas is Q2 will be positive. During the compression or cooling process, work is done by on the gas. Work is will be a negative, and internal energy of the gas will increase. Du change in internal energy will increase, and heat rejected by the gas will be the negative. Whenever gas is heated at constant pressure, the heat supplied to gas is utilized for the following purpose: to rise the temperature of gas mathematically, du is equals to mcpt2 minus T1. To do work during expansion, PV P V2 minus V1, which is equals to m or T2 minus T1. Constant volume law given by Gall's law, French scientist, and constant pressure law given by the Frenchman Jacques Charles. Here we can see that whenever heat is supplied to the system, internal energy of molecules will increase. That increase the entropy of the system also. We can see in the PV diagram of the isobaric process, whenever compression takes place at a constant pressure, volume of the system will decline, as well as the temperature of the system will increase. Other hand, whenever expansion process take place, volume of the system will increase, as well as the temperature of the system will decline. Increase in internal energy U2 minus U1 mcpt2. This is connected to the previous slides. Work done during the process or by the gases P2 minus V1 mcpt2 minus T1. When the gas is cooled at constant pressure, there will be a compression. The temperature and volume will decrease during cooling, and work is said to be done on the gas. In this case, heat rejected by the gas and decrease internal energy as well as work done on the gas. So this is all about today's lecture. Thanks for watching, and hopefully you will enjoy to it, and we will remain connected to each other. Thanks for watching.